about mental math and estimation. Okay, so be really careful that you do the right one in the right spot. That is to say, if it doesn't say estimate, don't estimate, and if it does say estimate, please do. Okay, because the directions are very clear, but just make sure that you're paying attention to what the directions say. So one of the things that it's going to talk about is mental math techniques. But in order for me to know what technique you used, and in many of the cases it will ask you, explain what you did. Okay, so please do that because I can't see the inner workings of your brain. So you have to explain to me what your brain did. So we're going to start with addition, okay? And the first mental math addition that we're going to work with is adding from left to right. And we've seen this a little bit, but I'm going to write the work down for it so that you can refer back to this and know what these methods look like as you're working. So when we add from left to right, what that means we do is that we add the tens digits in this case first. So we have 40 plus 30, and 40 plus 30 is 70. Thank you. And then we add the ones digits, 6 plus 8, and 6 plus 8 is 14. And then we add together the 70 plus the 14, and we get 84. And the way that goes is it's something that you can do in your head. There's no borrowing, or no, we're not even borrowing. There's no carrying. There's no values that exceed the number that you're working with. You're just doing it in your mind, right? So I could do 40 plus 30, that's 70. And then 6 plus 8 is 14, and 70 plus 14 is 84. Okay, that's mental math. Another one is breaking up and bridging. And so what we do on this one is we add the 46. So we take the whole 46. And what we add to this too is we sort of consider this 38 as 30 plus 8. Okay? So we're going to add to this 30. So what is 46 plus 30? 76. And then to the 76, after we've done that, we'll add the 8. Okay? 76 plus 8 is again 84. Now depending on what numbers are given, you may like one method versus the other. Okay? So that's okay. But this is a separate and different method. Okay? It's different than the first one, right? And there's certainly no carrying involved. Okay. Trading off. Now we've seen a method very similar to what I'm going to show you here. We call it equal additions. Okay? But we saw it when we did subtraction, not when we were doing addition. So let me show you what trading off looks like. Trading off still looks like taking one of these numbers, in this case it doesn't matter which one, and turning it into something with a 0 in the ones place. Okay, I want to have a 0 down there because it's easy to add when I have zeros. So you have two choices. One choice is to turn the bottom one into 40. But in addition, if I add 2 to one number, I would have to do the trading off, and what would I have to do to the other number? Subtract 2. Okay, I know that's not quite what we did with subtraction, right? Because it was subtraction. This is addition. Yeah.
Like add to the top one?
Yes, I'm going to show you that one in a minute. Absolutely, Jessica. So we could do this, then this would be 44 and 40 for a total of 84. So that's one option, and then just like Jessica mentioned, we could do 46. And what would you like to add to the top then, Jessica? 4. Would that be okay? Kayla suggested 4. You guys like 4 okay? Why would 4 be nice, Kayla?
Makes it
Makes it 50.
yeah.
It makes it have a 0 in the ones place, right? How about it makes it a multiple of 10? Multiple of 10. Okay. So this would become, what do we have? 50 here, like you said. But if I add 4 on top, then I have to subtract 4 on bottom. And 38 minus 4 is 34, and then I can add these just fine to give me 84. And there may be numbers in a certain situation where it would be nicer to add or subtract to one or the other. On this one, it's kind of a toss-up. There's really nothing better about one versus the other. But there are numbers where it would. Now, this method, compatible numbers, there was a couple of you who mentioned compatible numbers when the student was doing the work on the board with all the equal signs, and we had sort of the error and equals issues. But you mentioned compatible numbers. Compatible numbers is the idea that some numbers are nicer to add together than others. Okay? And it usually has to do with making things add up to values of tens or hundreds or something like that. For instance, what number is the nicest number on here to add to 40? 60, because 40 plus 60 is 100. Any other numbers that have that sort of a property? 30 and 70 those add up to, again, 100, and I haven't yet represented my 50 very well, so I need to include him for this, which would be a grand total of 250. And I can do that much quicker than adding that 40 plus 30 is 70, 70 plus 50 is 120, and then 120 plus 70 is 190, and then 190 plus 60 is 250, right? I have to think more instead of just pairing things up that easily add to 100. So that's compatible numbers. But as you can imagine, not every time do compatible numbers exist. So sometimes we want to make it exist, force them to be compatible. And if we force them to be compatible, what that means is we take either number, and it doesn't really matter which one. I'm going to use the top ones because I created the problem to use the top ones. What number very nicely adds to 35 to give you 100? 65. But I don't have 65, I have 68, right? So 35 plus 65 is 100, but how many have I not yet added to this? 3. So this is now 103. So in essence, I'm taking this and sort of breaking it apart into 65 and 3. And the reason I chose 65 was because it is a compatible number to 35. Now you may not think 65 and 35 are all that terribly compatible. If I were doing with 25 and 75, you might be more inclined to think they were, right? Okay, so there are numbers that probably ring a bell in your mind as, oh, those seem like they add together nicely. And others that may not quite so much. But that's compatible numbers, okay? And these are the different mental methods for addition. So we're ready to do subtraction now. Now notice some of the same names coming up again. So the first one is breaking up and bridging. So we're going to do the same kind of thing that we did just a minute ago. Instead of taking the numbers and trying to just flat out subtract them, we're going to take the first number and subtract the second number's 10th value. So not the whole 38, but the 30. So 46 minus 30 is 16. And then minus 8, because you probably know 16 minus 8 much more quickly without any borrowing involved, right? You should. All right, good. 8. So you get 8. So that's bridging, breaking up and bridging. Now trading off, this is the same as equal additions, okay? Very same thing. And so in equal additions, we wanted to make the bottom number something with a 0 in the ones place. So I don't have sort of flexibility I had when I did the addition. I really have to get that bottom number to be a 0 in the ones place, which means I really do have to add the number 2. And with subtraction, if I add 2 on bottom, I will add 2 on top. Okay, so if you have trouble remembering which one you add and which one you do subtractions, it might be a good thing for you to jot yourself down a note about. Maybe include on a note card for your test. Okay. All right, so 46 plus 2 is 48. 38 plus 2 is 40. Remember, this is subtraction, so I get a grand total of 8, just like I did a moment ago.
And we did plus 2, we did 40.
Exactly. We did. Okay. You guys ready for the next one?
Yes, ma'am.
Drop the zeros. You guys probably have done this before as well. Right, if I'm doing 4,600 and 3,400, do I really need to consider the zeros if I do this? No, I don't. I can really, in my mind, I'm just doing 46 minus 34, which is 12. And then the answer is 1,200 because I dropped the zeros and put them back on at the end. Yes,
Do we have to do it like that? Or draw a line?
I'm not sure how many times you're going to be asked to be dropping the zeros. I don't think it's all that exciting for the method. So if you don't do a lot of work on it, not too concerned. Most of the others, you're going to show something. I don't think you're going to encounter too much with that question. So, all right, and then we're done with subtraction. See how we're just flying through? You guys want to know if we finished today? All right, front end, I don't know, we'll see. We might. Front end multiplying. Okay, the way front end multiplying works, are you guys with me? Front end multiplying actually multiplies these with the first, this is kind of like left to right addition. We're actually taking this first number, and it is a 40, and we're multiplying 40 times 5, which is 200. And then we multiply the 6 times the 5, and we get 30. And then what do you think we do with the 200 and the 30? We add them to get a total of 230. Okay, so there's no carrying and adding in the middle of doing the multiplying. That's the nice thing about this. You can do it quickly without having to do any carrying. Okay, compatible numbers exist with multiplication just like it did with addition. So with addition, what we were looking for is pairing up certain numbers so that they equal tens or hundreds or something like that. We want to do the same kind of thing with this, but we don't want to pair them up so that they add up to 10 or 100. What do we want to pair them up to do? Multiply to get something that's nice, right? So what two numbers in this display, pick me two, multiply to give me something really nice? 8 times 5, okay? You could, if you want. I think there might be easier ones to work with. How about 5 times 2? 5 times 2 is 10. And I don't know about you, but 10 is a lot easier to multiply by than 25. Some people tell me 5 times 5. 5 times 5 is great, but I don't want to multiply with 25 on anything else. I like to avoid that, okay? So I'm going to group the 5 and the 2 together. And while it would be okay to do the 8 and the 5, I think the 4 and the 5 might be easier. Because 4 times 5 is 20, which would be easier to work with. So I'm going to rewrite this as 4 times 5. And then I've got this 8 in here, but I'll put him, I don't know, put him at the beginning. And then 5 times 2. We can rearrange all of that because of y. I use two properties at the same time. Associative and commutative. I use both of them. Commutative because I actually rearrange the numbers. Associative because I put parentheses in grouping things together. All right, so you guys just told me a minute ago that 4 times 5 is 20. And 5 times 2 is 10. And again, I want to avoid the 8 for a while. So if I do 20 times 10, that's 200. And that's really nice because I can do 8 times 200. And 8 times 200 is 1,600. And in some sense, I'm sort of dropping the zeros when I do that, aren't I? Yeah, I am ignoring those zeros for real when I do that. Okay, so you have to pause for a moment and consider what's the easiest thing to multiply, because you have lots of options. And you may not think of any of them as being terribly difficult, right? 5 times 5 is 25, great. 8 times 4 is 32. I mean, you can multiply all of those single digits in your head. But do you really want to do 32 times anything else afterwards? No. The answer is no, I don't. All right, the next one is thinking money, and there's not really any, I don't know why your book calls this thinking money. Well, I do know why it calls this, but you can actually do this without it being money related. So I'm going to go with what they're calling it. So we're going to think about it being as money. Okay, when you multiply by the number 5, you can think about it as being nickels. Okay? So we'll say i.e. we have 46 nickels. Okay, so is everybody with me? 46 times 5 cents, kind of an idea, 46 nickels. But it would be easier working with nickels, it would be easier to work with, okay, something else.
Dollars.
Dimes. Like we're doing the one on the board that you corrected on there, right? Where you said, oh, this is dimes, not pennies. The reason I don't want to change it into pennies, Kayla, is because that doesn't change the problem to help me in any way. But it helps me to think of it in terms of dimes. So in other words, this 5 would be easier to work with if it were a 10, wouldn't it? Yeah, it would be easier to be 10 because I like multiplying by 10. It's easier. Yeah? Yes. But do you remember when we did that equal additions and trading off? If I multiplied something by 2, I also would have to divide it by 2. Right? This is sort of that idea. So 46 nickels is the same as how many dimes? 23. And the reason it is because 46 divided by 2 is 23. You with me? All right, so how much is 23 dimes? 23 dimes. How much cents is that? How many pennies is that, Kayla? Somebody multiply 23 times 10. 230, thank you. Wow. Okay, so 23 times 10, right? 23 times 10 is easier than 46 times 5, isn't it? It's a lot easier.
Yes.
I mean, multiplying by 10 is fabulous, because all I gotta do is write down a 0 and then write down the same number I started with. So what do you think I might be doing when I'm gonna do this number times 25? It's quarters. So we think of as quarters. So imagine you are a bubblegum machine vendor and you ended up having 44 quarters come out of that machine when you went and serviced your machines, which by the way my grandfather did. He owned a bubblegum machine business. So if I change this, so we have 44 quarters. How many dollars is that?
11.
That's $11, right? Because there's 4 quarters in a dollar. Yeah?
Yes.
So if I have $11, how many, we'll say pennies or whatever, how many coins? Coins isn't good. How many cents is it? 1,100, right? And in essence, what you're doing with the numbers over here is that you're multiplying this by 4 to get 100, so that you can divide this by 4 and have 11. 11 times 100 is 1 with 2 zeros.
Let me get all this stuff. I just don't know.
Well, and the reason I bring up this over here is because this idea of multiplying and dividing works with any numbers. It doesn't have to be something about coins. Okay? So the idea of multiplying by 4, dividing by 4, multiplying by 6, dividing by 6, whatever the numbers are you work with, it works for anything. This idea over here would be restricted only to the idea of working with money. We can do the same if you wanted to multiply by, what did they did? 2. Okay, that's not what I did. There's another example that your book did besides 5s and your 25s. You can take a look. Anyway, so this is thinking money. Okay, so if you think about your coin, think about your multiplication as money. Again, this is awfully specific, right? I mean, in the grand scheme of things, how often do we multiply by 5 or 25? Not all the time. So that doesn't work on every problem. But when it does work, it's kind of nice. You can think about it in money and in that way. All right. Division, mental math division. All right, so the first one for mental math division is breaking up the dividend. Which one of those two numbers is the dividend? No. The big one. Thank you, Lauren. All right. This is the dividend. This is called the divisor. And then the answer to a division problem is called a quotient. Somebody said it. Who said it? Thank you. Quotient. All right. So those are the 3 words for division that you need to know: dividend, divisor, and quotient. So we're looking for the quotient. We're going to break up the dividend. That's the 6318. So imagine old-fashioned division written like this, right? Here's the idea. You break this apart in the middle so that you're expressing this as 6,300 plus 18. Okay? This is the idea. So you divide 9 divided by 6,300 and 9 divided into 18. So what is 9 into 6,300? 700, right? And 9 into 18 is 2. And what do you think you do with the 700 and the 2? You add them. 702. Not bad. Okay, so that's one way. Again, that's awfully specific. I mean, it was really nice that I gave you 63 and 18, right? And sometimes the numbers do work out nicely, and you can use that. All right, compatible numbers. All right, so compatible numbers is similar. It's similar rather to the breaking up the dividend. Okay, so I want to be able to write this as 5 into 425. But I can't sort of break it at the 4 or the 2 and go in nice and neat and pretty like, right? That's exactly what we do. So we break this apart in a way that is nice. And 425 is nice. So we divide the 5 into 400, and we divide the 5 into 25. So 5 into 400 is 80. 5 into 25 is, and what do I do with the 80 and 5? I add them to give me 85. You guys are punchy today. Yes. You just get a kick out of everything. All right. What happened on this slide? What keyword is different?
Estimation.
Estimation. So am I going to get exact answers on these particular problems? No, I am not going to get exact answers on these problems. This is estimation. This is what you do at the grocery store to make sure that when you get up to the register, you don't have to put something from the cart back on the shelf. Right? I know, it is what you do, I know. That way you don't have to pull out your credit card or your check card or whatever. All right, so the first one is front end with adjustment. Now, we've talked about front end in here, I think. Yeah, I talk about it now, since like every class. Have we not talked about front end estimation? Okay. The way front end estimation works is front end estimation adds the first digits together. Okay? So you're adding this as though it's 300, 400, 200. Okay, this is not rounding at all, right? Okay, because I did not consider what the rest of the numbers were at all. All I did was turn them all into zeros. All right, so 300 plus 400 plus 200 is 900. Okay, so that is front end estimation. Okay, so this is the front end part. All right, so the adjustment part's what I'm going to do next. The adjustment part takes the ends of these numbers and it looks to see what they approximately are. Okay, so we might be looking for nearly or compatible or nearly compatible numbers. In fact, we have a pair of them. There are two numbers here that are nearly compatible numbers. What are they? The 32 and the 62 are nearly compatible. And what would they add to? That's what they exactly add to. What would they approximately add to? They're nearly 100. Nearly 100. These two right here, they're about 100. Okay, we're not interested in being exact, we're approximating, right? I don't want to keep 94 in my head, I'd rather add 100. The 25 at the end I'm fine with, because I have 900, 125, which gives me a total of 1,025. It's an approximation, but it's a pretty good one. It's not bad, right? In fact, you know exactly how much we're off by because you guys are doing it in your head for real. How much are we off by? 6. Because it wasn't really 94, wasn't it? We're really off by 6. All right, grouping to nice numbers. That's a compatible numbers issue as well. This is the language your book uses, so I'm using it. But grouping to nice numbers. We want to look for numbers that are nearly compatible. So, do you see some?
71.
Which one?
35 and 35.
All right, 35 and 71 are nearly
100.
100. What else? Somebody said something
64
else.
and 42.
64 and 42 are nearly 100, and 55 is about 50, so this is about 250. You don't have to like estimation, but you're going to have to teach it if you teach anything above about second grade. Okay.
So I'm doing first.
Well, you think you're doing first, but I bet your certificate says otherwise.
No.
All right. What else do we have?
Second grade position, no. I refuse.
Okay. Let me do clustering, and then I'll have 1, 2, 3, 4 more to do next time, which will be really quick. You'll have a chance to do group work next time, okay? Clustering's our last one then for today. Clustering, again, this is one of those ones that does not work for everything, but when it does work, it's really nice. Clustering means when you look at the numbers, they all look like they're really close to the same kind of value. They're all approximately surrounding the number
500.
500, aren't they?
Yeah.
Those numbers are all really close to 500. So this, again, this doesn't work all the time, but these are all approximately 500. So you can take 500 times 5 for 2,500. That's an approximation, which is all we're doing anyway, of the numbers. So when they all tend to cluster around the same value, multiplication, because it's like repeated addition, right, will work. All right, so we'll do the other 3, 4, I think it was 4 next time.